Yes, connection is okay.
Yes, sir.
Yes,
Screen is visible.
sir, not visible at this time.
No, sir.
Yes, now.
Yes. Yes, sir, now visible.
Yes, let A belongs to M2. Let an eigenvalue of A be on the main diagonal of A. Show that at least one of the off diagonal entries of A must be 0. This is a very simple question, nothing to do with numerical range. Anybody? Anyone want to comment? No? तो आगे नहीं. Next कैसे है? Yes, this is simple. Take lambda 1, lambda 2 eigen of value of these 2 by 2 matrix. If lambda 1 is on the diagonal, then we can write A in this form. For this matrix, trace of A is sum of diagonal entries. And this is also equal to sum of eigenvalues. This means A22 must be lambda 2. So A is lambda 1, lambda 2, A12, A21. Now the characteristic polynomial of this is x square minus lambda 1 plus lambda 2x, and then determinant. This is trace of this, and then determinant lambda 1, lambda 2 minus A12, A21 is equal to 0. Also, the characteristic polynomial having eigenvalues lambda 1, lambda 2 is this. X square minus lambda 1 plus lambda 2x plus lambda 1, lambda 2 is equal to 0. Now, if we compare these two, what we have, this product A12, A21 is 0. So either A12 is 0 or A21 is 0. Yes. But this is not always true when n is greater than or equal to 3. For example, we have this matrix. Determinant of this is 0 because these two are linearly dependent rows. So 0 is one of the eigenvalues. But note here that A12 and A13 are not equal to 0. Clear this question?
Yes, sir.
Now show that any ellipse is the numerical range of some matrix A belonging to M2. We can take A to be this ellipse, A plus B, A minus B. A and B are non-negative, A is greater than or equal to B. And then we see A star this, A star A this. So A is not normal. Hence WA is non-degenerate ellipse. Length of major axis, this is the formula. We calculate this comes out to be 2A. Length of minor axis, this comes out to be 2B. So numerical range is this ellipse. Now any ellipse in the plane can be translated to this ellipse on choosing appropriate values of A and B. Hence any ellipse is the numerical range of some 2 by 2 matrix. Now, sixth question. Anybody want to comment? If WA is in right half plane, that is open right half plane, then WA inverse is also in open right half plane. Since WA is in right half plane, therefore numerical range of A is also in right half plane. Eigenvalues are all positive. So we can have this A inverse. Yes, anybody want to think of thing? What is that? No? Now note here, WA is contained in right half plane. This means real part of numerical range is in right half plane. So numerical range of A plus A star by 2 by projection property. This is equal to numerical range of A plus A star by 2. This is also in right half plane. This implies A plus A star by 2 is positive definite matrix. Because this already is Hermitian, numerical range is in right half plane, therefore all its eigenvalues are positive. So this is a positive definite matrix. Now if matrix is positive definite, then its inverse is also positive definite. We will discuss this in detail tomorrow. So also then we can write A plus A star as A star minus plus A inverse A star, because when we take this inside, we get this matrix. So now taking inverse of this equal A star inverse, then A star inverse plus A inverse by 2 whole inverse, then A inverse. This is positive definite matrix. Now, if A is positive definite, then X star AX is also positive definite. So here we can take A star, multiply with A star, and here with A. So we get A inverse star plus A inverse star by 2 is positive definite. So this means A inverse star plus A inverse star by 2 numerical range is strictly positive. So real part is of numerical range of A inverse is in right half plane. This means numerical range of A inverse is also in right half plane. Clear this?
Yes, sir.
Yes, this question, anybody want to comment? Let A belongs to Mn, then lambda minimum of A plus A star by 2 less than equal to real part of lambda K A less than equal to lambda maximum of A plus A star by 2. And lambda minimum of A minus A star by 2 iota less than equal to imaginary part lambda K less than equal to lambda maximum of A minus A star by 2 iota. Yes, anybody participant wants to comment?
Real part of WA is equal to WA plus A star by 2, and all eigenvalues of A belongs to WA. So real part of WKA is in between minimum of A plus A star by 2 and max of A plus A star by 2. Since
Yes,
for each
good.
hard is the length of mean.
Yes, good. By projection property, numerical range of A plus A star by 2 is equal to real part of numerical range of A. And this is real part of X star, AX, X star, X is 1. It follows that if X is a unit eigenvector correspond to eigenvalue lambda K, then real part of X star AX is equal to real part of lambda K. Therefore, real part of lambda K belongs to numerical range of A plus A star by numerical range of A plus A star by 2. Now this matrix is Hermitian. So its numerical range is this interval. Line segment joining smallest and largest eigenvalue of this. And so real part of lambda K belongs to this interval. The second inequality follows similarly. Or we can visualize this in this way. This is numerical range of A. Now, numerical range of A contains spectrum. So lambda K is somewhere here. Suppose it is here. Then this is its real part. Also by projection property, this interval line segment from lambda minimum of a plus a star by 2 up to lambda maximum of a plus a star by 2 is this. So real part of lambda k, a will always be greater than equal to lambda minimum of a plus a star by 2 and is less than equal to lambda maximum of a plus a star by 2. This also shows that on studying numerical range, we get insight into the structure of matrices. For example, this immediately provide this bound. Otherwise, it is slightly difficult to prove such type of inequality. Similarly, we can argue for this second inequality. Yes, this is not for numerical range, but we need this question to use this in next question. Yes, anybody want to comment? Let alpha be the convex combination of real numbers x1, x2, xn. That is, alpha is equal to some pi xi. Pi are non-negative and some pi is equal to 1. Let minimum of I xi, this is x1, or we can take any, just we take this to be x1. If alpha is equal to x1, then p2, p3 up to pn are all 0 and p1 is 1. If alpha is equal to xn, then p1, p2, pn minus 1 are all 0 and pn is 1. Yes, any participant want to discuss or comment on this? I have put all these questions in Dropbox. So from a different point of view, note this question as if we this some pi xi, this also from a statistical point of view, this is just arithmetic mean of these numbers x1, x2, xn. And what we have arithmetic mean always lies between smallest and largest of these n real number. Say x1 is smallest, xn is largest. So this arithmetic mean lies between x1 and xn. So in this question, what we have, this equal minimum. That is, this arithmetic means equal minimum of xi. If p2, p3, pn are all 0 and p1 is 1. And likewise, this arithmetic mean is equal to largest of xi if all these pi's are 0 and pn is 1. Want to comment anyone or solve full question? This is very simple. Say this x1 p1 plus x2 p2 plus xn p1, this equal x1. Since p1 plus p2 plus pn is 1, therefore we can write this as x1 p1 plus p2 plus so on up to pn. Now this x1 p1 cancels out from here, and other terms can be grouped as x2 p2 minus x1 p2. This equal x2 minus x1 p2 plus so on up to xn minus x2 pn is equal to 0. So net etc. are okay. Are you listening to me?
Yes, sir. Yes, sir.
Okay. So x2 minus x1 p2 plus so on up to xn minus x. Okay, thank
How
you.
x1 is less than xi for I equals to 2?
Yes.
It might be possible that x1 is equals to x2 as well.
X1 is equal to
X2.
yes.
Because we are not taking the distinct real numbers.
Yes, here we are taking this is minimum of this. Just x1 is minimum. Also note that if they are not equal, then instead of this we consider different expression x1 plus x2, then p1 plus p2 and up to pn minus 1. If all are equal, then we have done, because these are 0 and P1 is 1. If two are different, then we can write in this form. So point is that here we get positive. And since P1, P2, Pn are all non-negative, therefore this sum is equal to 0 gives P2, P3, Pn equal to 0. Clear this? Yes, for more clarity, we can mention that all xi's are distinct. Yes, any further comment? Now, same argument when alpha is equal to xn, then x1 p1 plus x2 p2 plus xn pn, we can write in this form. So xn pn here cancels out. So xn minus x1 pn plus on up to xn minus 1 pn minus 1. Again, for same argument, we have p1, p2 up to pn minus 1 are 0 and pn is equal to 1. Clear this?
Yes, sir.
Yes, we need this last exercise to discuss this 9th. Let A belonging to M and be Hermitian. Then note its eigenvalues are real. Let X belonging to C and be a unit vector. Show that X star AX is equal to lambda maximum of A or lambda minimum of A, if and only if X is eigenvector of A, corresponds to eigenvalue lambda maximum or lambda minimum A. Yes, anyone want to comment? Now, if
X star
yes,
is equal to lambda max x, this implies that if we multiply these two are scalars, if we multiply x star ax equal to
yes,
lambda ax, now
yes.
x star is 1, so ax equal to lambda max ax. This implies that x is an eigenvector for lambda max A.
No, from one side it is okay. If AX is equal to lambda x, we can take X to be unit vector, unit eigenvector. AX is equal to lambda x, then X star AX is equal to lambda X star x. So X star AX is equal to lambda. This is okay from one side. Now, what is about converse? If X star AX equal largest eigenvalue or smallest eigenvalue, then X is going to be eigenvector. This is important. If X star AX is equal to largest eigenvalue for some X, then X is going to be eigenvector. Yes, anyone want to comment on converse part?
Star ax and lambda max A both are scalar. So we x star ax equal to x lambda max A. No.
Sir, this way, as A is Hermitian matrix, so all its eigenvalue are real number,
Yes.
and X star AX is lie on a numerical range.
Yes.
Numerical range of Hermitian matrix is the set of all the eigenvalue which lie on a real. So
Yes.
it's minimum eigenvalue or maximum eigenvalue is any of this X star AX which lie on a real line.
No.
But point is how this X vector is that X vector should be a eigenvector.
Yes.
Mm.
Yes, anyone more? Yes, we prove converse part. From one direction, it is simple. If we have x star ax is equal to lambda x and ax is equal to lambda x, we put here, this is satisfied. Converse part, we take x star ax to be the largest eigenvalue. The arguments are same when we take the smallest eigenvalues. Now, since A is Hermitian, it is normal. And spectral theorem, consequence of spectral theorem says that A has an orthonormal set of eigenvectors. So we can write X as C1 U1 plus C2 U2 plus Cn Un. We are taking U1, U2, Un to be orthonormal eigenvectors in Cn. So any vector X then can be written in this form because this is a basis then. Also note that x star x is 1. Also these are orthonormal, therefore ui star uj is 0 for I not equal to j. And ui star ui, this comes out to be 1 because this is a unit vector. Now we calculate this x star x, which is 1. We put value of this C1 conjugate, then U1 star plus C2 conjugate, U2 star plus on up to Cn conjugate Un star, then this vector x. Now multiply these two. We have C1 conjugate, C1 is mod C1 square. U1 star U1 is 1. So first term is mod C1 square. Now multiply U1 star with U2. This is 0 because these UIs are orthonormal. All others are 0. That is ui star un is also 0 and so on. Now come to this second. U2 star U1 is 0. And then U2 star U2 is 1. Therefore, this equal mod C2 square plus so on up to this last mod Cn square. So this sum is 1. Now we calculate x star ax. C1 U1 plus C2 U2 plus Cn Un star. And here C1 A U1 plus C2 A U2 plus Cn A U N. Here we are writing this just x and then star. And here we are writing Ax. Now these are the eigenvector. This corresponds to eigenvalue lambda 1. AU2 is lambda 2 U2. An Un is lambda n Un. Now again multiplies this. This is just scalar C1 lambda 1 and U1 star U1 is 1. So this is mod C1 square lambda 1 plus mod C2 square lambda 2 up to mod Cn square lambda n. Now use this last exercise. What we are saying, if this expression is equal to largest eigenvalue, say lambda n, lambda maximum we take to be lambda n. Then by this last exercise, C1, C2 up to Cn minus 1 are all 0. So C1, C2 up to Cn minus 1 are all 0. So what remains in x? X becomes equals to Cn Un. And Un is eigenvector of A, corresponds to eigenvalue lambda n. So this x Cn Un is also eigenvector of lambda n. Clear this? So
Yeah,
x eigenvector of A correspond to lambda maximum. The arguments are same when we replace lambda maximum A by lambda minimum A. So this is important exercise, that x star Ax is equal to lambda maximum A when A is Hermitian if and only if x is eigenvector. Now one can note that this does not hold good when we take any other value. That is x star Ax is suppose equal to lambda 3, which is not neither largest nor smallest. Then obviously it is achieved at eigenvector, but also achieved at some other vector. For example, consider this simple matrix. x1, x2, x3. This equal 2 times x1, x2, x3. Multiply these two, we have this. 3x2 is equal to 2x3. So x3 0 and x1 is equal to 2x1, x1 0. From here, this is 1, 0, 1, 0 is eigenvector of A. And so we calculate this x star Ax, this comes out to be 2.
2.
Now we take x to be this vector, 1 by root 2, 0, 1 by root 2 transpose. Now we calculate this, this is not an eigenvector. Why? Because if we multiply this, we get 1 by root 2, 0, then 3 by root 2. And again multiply by this, we get 1 by 2 plus 3 by 2 equal to 2. So from this example, we see that any eigenvalue which is neither largest nor smallest may be achieved by either eigenvector or any other vector, unit vector.
Unit vector.
Largest and smallest are achieved only when x is unit eigenvector.
Vector.
Clear this question?
Yes, sir. Yes, sir.
Yes. Next, let A belonging to Mn be Hermitian. If the largest, smallest eigenvalue of A lie on the diagonal AKK of A, then AKJ is equal to 0 for J1 to up to N. K not equal to J. This means given that A is Hermitian matrix, and we suppose that the diagonal entry is the largest eigenvalue or smallest eigenvalue. Say first diagonal entry is the largest eigenvalue. Then all the other entries in first row and first column are all 0. Yes, anyone want to comment?
Yes, sir. We can take the vector as x equals to ek. Then ax is equals to akk ek. And we will take the transpose, then it will be ek star, a star. A star is A. And that is equals to akk x star.
Yes,
It is
very
AK
good.
star. Then from there we can answer.
Yes, good. Proof this. We take this vector x. First 1, 0, 0. Then as already discussed before, x star Ax comes out to be A1, 1. Correct? And we are saying this A1, 1 is the largest eigenvalue. Therefore, by above exercise, this must be eigenvector.
Vector.
Because we have discussed that this largest or smallest is achieved only when x here is eigenvector. Now take this to be eigenvector 1, 0, 0, so on up to here. So when we multiply this, we get in left hand side this column vector and in right hand side this column vector. So A1 is equal to A1 is okay. Otherwise A1 to A1 3 all
Should be 0.
these are 0. And since it is Hermitian, the corresponding entry is A21, that is A12 conjugate up to A1 and conjugate are 0.
0.
So this is just first entry, and otherwise in general we can take x to be ek, where ek is this column vector whose kth entry is
1 and other.
1 and all other entries are 0. Then we again get that all the off diagonal entries in that row and column are 0. Now this is not true if we have largest or smallest eigenvalue. For example, we take A to be this matrix. Its determinant is 0 because these two rows are linearly dependent. So this means 0 is going to be eigenvalues. But here A12, A13 not equal to 0. This means 0 is not neither the largest nor the smallest eigenvalue of A. Correct? Because also see from here, this principal submatrix is non-negative. So this matrix A has one negative eigenvalue, one eigen is 0, eigenvalue is 0, and one eigenvalue is positive. So 0 is the middle one eigenvalue. So in this case, this previous result does not hold good. Yes, show that the numerical range of this matrix, where Z is a complex number with modulus 1, is a closed region bounded by equilateral triangle, whose vertices are the cube roots of Z. Yes, participants, anyone want to comment? Yes, we have A star. If we multiply this is A star, we get this matrix. And A star A, this matrix. What is given? Modulus is given to be 1. With modulus 1. Z is a complex number with modulus 1. So A star is identity, then A star A also identity. This means A is normal.
Normal.
Therefore, its numerical range is going to be the convex hull of the eigenvalues. The numerical range of a normal matrix is the convex hull of the eigenvalues of A. Now, if characteristic polynomial of this matrix is lambda cube minus Z is equal to 0. So its eigenvalues are this cube roots of Z, and then convex hull of these eigenvalues is numerical range of A. Otherwise, you can explain like this. Yes, question number 12. It is simple. Yes, anybody want to comment?
Sir, answer is mod of Z minus 1 is less than equal to 1 by 2.
Less than equal to 1 by 2. Yes, answer is, I think, this. How? Explain.
Simply calculated the x star ax, where x is equal to vector z1 bar z, x is z1 z2, and calculate this comes out to be x star ax is equal to z minus 1 is equal to z1 bar z2.
Yes, good. Also, we can calculate now. To find the numerical range, we have already discussed the numerical range of 2 by 2 matrices. We can discuss it from that point of view. Eigenvalues are same. So numerical range is going to be, as we have discussed in first talk, if eigenvalues are same, then numerical range is disk. Numerical range is disk. And what is the center? Trace A by 2. So 1 plus 1 by 2, that is 1 is going to be the center. Now we have to calculate radius. because it is slightly lengthy. It is okay, you have solved this question, but it is lengthy to calculate this x star A, then x. Now, this is the diameter of then this is length of major axis of ellipse. Now, in case of disk or circle, this becomes diameter, trace B star B plus 2 mod determinant B. B is this matrix A minus trace A by 2 I. 0, 0, I determinant is 0. So this part vanishes. Only we have trace B star B. Trace B star B is sum of the modulus of square of each entries. So this is just 1. So this is 1. This means diameter is 1. And center, we have already discussed, is 1. So this is mod z minus 1 less than equal to half. Same answer as one participant was telling. Yes, question number 13. Show that the numerical range of A belonging to Mn is constant if and only if A is a scalar matrix. Could WA consist of two distinct points only? First, try to answer this second part. Could WA consist of
if it consists 2 points, then it must contain the line segment corresponding to that and because of the convex hull.
Yes. All so numerical range is a convex set in connected set. If we have only two distinct points, only this means they are not connected. So it is not possible. Good reply. Now try this part. Show that the numerical range is constant if and only if A is a scalar matrix. If A is a scalar matrix, then numerical range x star AX is just in place of A, write alpha x star alpha x, which is just alpha x star x is 1, which is just alpha. So one part is immediate. Now conversely, suppose numerical range is constant. Say this alpha 1 point. Then x star AX is alpha for all x belongs to Cn. Choose x to be this column vector. Then x star AX is equal to alpha gives A11 is equal to alpha. Likewise, on choosing general EK, we have AII is equal to alpha. So each diagonal entry is alpha. So we can write A in this form. A is equal to alpha I plus B. Now all the diagonal entries of B are 0, and off diagonal entries of B are same as that of A. So now numerical range of A by translation property is alpha plus numerical range of B. We have to show that numerical range of B, if numerical range of B is 0, then B is 0. WB is 0. Now take X this vector, unit vector. 1 by root 2, 1, 1, 0, 0. So from this we get this expression A12 plus A21 is 0. And from x is equal to 1 by root 2, 1 minus 1, 0, 0, we get A12 minus A21 is 0. So A12 is equal to A21 is equal to 0. Likewise, if we take this matrix 1, 0, 1, and then next vector 1, 0, 0, 1, etc., we find that all Aij and Aj are 0. So this proves the result that A is a scalar matrix. Yes, if A belonging to Mn and alpha belonging to numerical range, any point, then there is a unitary matrix such that alpha is 1, 1 entry of U star A U. Yes, anybody want to comment? That is any point in the numerical range. If alpha is any point in the numerical range, then it can be brought to 1-1 diagonal entry, such that then this is the 1-1 diagonal entry of a matrix which is unitarily similar to matrix A. Suppose alpha is in numerical range, then alpha is equal to x star ax for some unit vector x belonging to Cn. Now we show here that x is equal to uy for some unitary u, where y is this 1, 0, 0 transpose this vector. Why? Because then we put here x is equal to uy, and this will become y star u star. From that we see that 1-1 entry is then alpha. Now x is a unit vector, we denote it by u1. And we can extend u1 to orthonormal basis u1, u2, u1. So this matrix is then unitary matrix u1, u2 up to un. Now calculate u star u1. Yes, what is this product? Because this is unitary, the rows and columns are orthonormal. So this mod u1 square plus mod u2 1 square up to plus mod un 1 square, this comes out to be 1. And all other products are 0 because of orthogonality. So u star u1 is equal to this column vector 1, 0, 0, so on. So multiply with u, we have u1, that is x is equal to u time this u1. So alpha is our x star ax. In place of x, write uy. This uy star. This comes out to be y star u star. Take y u star here, a, then take y u here, y. This y is 1, 0, 0, so on, and also here. And what this gives? This gives 1-1 entry of this inside matrix. Clear this? Clear?
Yes, sir.
Am I audible?
Yes, sir.
Yes, sir.
Clear this question? Okay. The questions were, some of the questions were simple. Yes, in tomorrow tutorial, we will keep some more simple questions. So say this 15th. Every complex square matrix is unitarily similar to a matrix whose diagonal entries are all equal. Yes, take this and try to solve in next tutorial. For the tomorrow tutorial, I will try to put some simple, more simple questions. Every complex square matrix is unitarily similar to a matrix whose diagonal entries are all equal. This is a very important result. That is, if a matrix is given, we can find a unitary such that u star, diagonal entries of u star au are all equal. This you can try and we will discuss in next result, next tutorial. Yes, any more comments or discussion from the audience side?